So now we're going to talk about graphing quadratic functions, all right? And graphing parabolas that open either up or down. Um, the first thing we want to look at is what the vertex of a function is. Now, a vertex of a function is the point where the graph of a function changes from either being decreasing to increasing or from being increasing to decreasing. So a parabola has a specific point, only one point that you can call its vertex, right there, that point at the origin that I'm coloring green. So as you can see on the left side of that point, the functional values, the y values are decreasing, and on the right side of that point, the functional values are increasing. So it's decreasing on the left and increasing on the right, making that point a vertex for the parabola. Now, other functions may have more than just that one vertice, but a parabola, a quadratic function, only has one vertex. Now, this is what we're talking about, the quadratic function. F of x equals ax squared plus bx plus c. This is also a quadratic function. This one up here is written in what's called standard form. It's like a general polynomial expression. But this one down here is written in what is called the vertex form. All right, so what is the relationship? H and K would give you the values where you would move this vertex for this particular parabola. This particular parabola is just a squaring function. This one has its vertex at the point 0, 0. But other parabolas that aren't as simple as this one, that have other terms, for instance, linear and constant terms, would have vertexes that were not at the point 0, 0. And if you wanted to find the vertex of those parabolas, you would want to look at this vertex form because the vertex would be hk. So the point where the vertex would move from 0, 0, instead of 0, 0, it would be the point h comma k for the vertex. This would be the vertex, all right? Now let's say you're given a quadratic function in the standard form up here. How can you find h and k is the question. Well, it turns out that there are formulas for h and k that you can use to find the values of h and k. And if you know h and k, you know where the vertex of the parabola moves to. So the value for h, the x value of the vertex of a parabola, is equal to negative b over 2 times a. Negative b over 2 times a. So here's b in the standard form. Here's a in the standard form. We're just going to take the opposite of b and divide it by twice a, 2 times a. And the value of k, well, there's a couple ways of going about this. You could actually, once you found the value of h, just plug it in for x here to find out what the value of k is. But there's also a formula for the value of k. K is equal to c, the constant, minus b squared over 4a. 4a. So if you want, if you have a parabola that's in the standard form and you want to know where the vertex of the parabola is, then all you have to do is find h as negative b over 2a, and you can either plug that value of h in to find the value of k, or you can use this formula to find the value of k. All right. So once you have that, this is what happens. The parabola y equals x squared, which would be this one here, which is centered at 0, 0. Well, the vertex of that parabola would move h units horizontally and k units vertically. So this point here, the point that's at 0, 0, would now move to another point. It would be h units horizontally and k units vertically. So instead of having its vertex be at the origin, the vertex would actually move h units, well, from here, it would move h units horizontally and k units vertically. And that's where the new vertex for the parabola would be. And that's why that is called the vertex formula, because it allows the vertex now to rest at h comma k, that ordered pair. Now the other points are also related, because once you find the vertex, you know that if you go one to the right, of the vertex, there is a point that is 1 unit up, just like on the y equals x squared, because if you square 1, if you plug in 1 for x, you get 1 for y. 1 squared is 1. So from the vertex, if you go 1 unit to the right, you would go 1 unit up. Also, from the vertex, if you go 2 units to the right, well, if you square 2, you get 4, so you would go 4 units up. So even after you've moved it to HK, if you go 2 units to the right, you would still go 4 units up to locate that next point. What about these other points over here? Well, parabolas actually have what is called the symmetry. They display symmetry, and the line of symmetry here is actually this vertical line right here. If you take a look at that vertical line, you'll see that this parabola has a mirror image on the left of that dashed line I just draw, that dashed vertical line. On the right side and on the left side, you pretty much have a mirror image. Now, for the original squaring function, the axis of symmetry is the line of symmetry is the y-axis. But once you translated the vertex, h units to the horizontal and k units vertically, the new line of symmetry for that parabola that you draw, which is called the axis of symmetry, um, actually shifts over h units in the horizontal direction. Okay, so this is the slide here about the axis of symmetry. So we find out that the axis of symmetry of a parabola, if there is a horizontal shift, the value of h, which is equal to negative b over 2a, the value of h is actually where the line of symmetry moves to. So the line of symmetry, or the axis of symmetry for a parabola, is going to be the line, the vertical line, x is equal to whatever that value of h is that you found. So looking back at it here, here it is. The vertex now moves to hk from 0, 0, horizontally h units, vertically k units, but you still have this vertical line, the line of symmetry, which is the line x equals h. So that's how you find the axis of a parabola. X equals h. Okay, so we've discussed h and k from this formula, the vertex formula. H and k are the horizontal and vertical translations respectively. But what about the other thing, the other number over here, a? Well, what a does is a is actually the vertical shrink or stretch. For instance, well, we had this original parabola here which had this is y equals x squared. If you plug 1 in, you get 1, right? And if you plug 2 in, when x is 2, you get y is equal to 4. 4. So, I mean, this is that original parabola. How does putting something in front, what does that do? Well, it's a stretching or shrinking factor. You're going to stretch or shrink by the value of a. So, for instance, for this parabola, let's say we wanted to graph y is equal to, I don't know, 2x squared. Well, the original one, the blue one, is just the parabola y equals x squared. The difference between the blue one and the red one I'm about to draw is that all the y values for the red one are going to be twice as much as the y values for the blue one. Well, you still get the point 0, 0. 0, 0, because 0 squared times 2 is 0. But when you plug in 1, 1 squared is 1, 1 times 2 is 2, so I don't get the point 1, 1 like I did for the original parabola. I get the point 1, 2. It's twice as high as the one on the blue parabola. And then when I plug in 2, 2 squared is 4, 4 times 2 is 8. So I'd be all the way up at 2, all the way up at 8, twice as high as I was before. And you get a parabola on the right-hand side that is a lot steeper than the blue one. It curves upward more drastically. So this is a skinnier U. And because of the line of symmetry, I know I have an identical point on this side here because it's symmetric to that point. And I also have a symmetric point on the other side of the line of symmetry, the y-axis here. So I know that my u now is just a taller, skinnier u, but it's still a parabola, it's still the shape of a u. So you see, a factor in front of the function will stretch the function out, making it taller and skinnier if that fraction or if that number a is a number greater than 1, and it'll make it shorter and fatter if that number a is a number between 0 and 1. Now, what we haven't discussed is what if a is a negative number? What if a is negative? Well, let's see. If a is negative, if a is less than 0, then, well, let's take a look at this one here. What if a is y equals negative, let's say 2x. Let's say negative 2x. And actually, let's graph that. Let's graph that in red. Y equals negative 2x. Well, what that has the propensity to do is, well, you still get the point 0, 0 on there, but when you go 1 to the right, instead of going to 1, 1, 1, you're going to go to 1, and then when you square the 1, 1 squared is 1, but then you're going to multiply by negative 2. So instead of going up, you're actually going to go 2 units down. 2 units down. And the same when you plug in 2. If you plug in 2, you get 2 squared is 4. 4 times negative 2 is actually negative 8. So you're actually going all the way down to negative 8. And you get something that is an upside down parabola. So whenever the value of a is negative, and of course because of symmetry, you have these 2 points on the left side. Whenever you graph a parabola where the value of a is negative, you're going to get a parabola that opens upside down. Instead of a u, it's going to be an upside down u. All right? So there you have the effects of those things. When we have 3 things going on here, we have the translation horizontally and vertically, and we also have this stretching that can also flip the thing over. All right, so let's take a look at a problem here. So what I want to do is I want to graph this quadratic function, identifying the vertex, the axis of symmetry, the domain and the range, and also any intercepts. So let's go ahead and do that. The first thing I want to do is I'm going to identify the vertex. Well, the vertex, h, remember h was negative b over 2a. So h is actually equal to negative 12, because 12 is b, over 2 times negative 2, because negative 2 is a. And then we get that this is equal to negative 12 over negative 4 or positive 3. So this is the horizontal translation. The x value of my vertex is going to be 3. K now, I'm going to find k, which is the y value of the vertex. And you can either just plug it in, or you can do the calculation c, which let's write the formula, actually. The formula is going to say c minus b squared over 4a. And let's see what this yields. C is negative 16. And this is going to be minus b squared, which is 12 squared, over 4 times a, which is 4 times negative 2. And this is equal to negative 16 plus, because 4 times negative 2 is negative 8, 144 over 8. So that seems to me 144 over 8 is 18. So we get negative 16 plus 18. And I find the y value of the vertex to be 2. So now I know the vertex of my parabola. The vertex of my parabola is hk, which in this case is going to be 3 comma 2. So the entire parabola will be shifted 3 units to the right and 2 units up. The other number that I need to know is a. But if you notice back here, when I gave the initial two formulas, I use a for both the leading coefficient here and the coefficient in the front here. That's because they're the same value. So the leading coefficient in the standard form will be the same leading coefficient you get when you put it in the vertex form. Therefore, I know the value of a also for the graph of this parabola. I know that a is the number -2. -2 is the value of a. All right, so a is -2. All right, so here's what I'm going to do first. First, I'm going to see how this parabola is going to be stretched out. I'm going to see if it's reflected. And then I'm just going to move the vertex of that stretched out and reflected parabola to 3 comma 2. All right, so let's take a look at what that parabola looks like. Well, let's get ourselves an x and y axis. Here, I'll let this be my y-axis. Let's just change this to an arrowhead. And, okay, didn't do that. Change this to an arrowhead here too. So there's my y-axis. Okay, here once again, right, is my y-axis. And here is my x-axis. Okay, oops, that one's a little crooked. Make another x-axis. So what I'm going to do here is I'm going to go ahead and I'm going to graph the squaring function, the most basic quadratic function, which is just y equals x squared. 1, 2, 1, 2, 1, 2, 3, 4. 1, 2, 3, 4. All right, so the squaring function, the most basic parabola there is just y equals x squared. We're going to use that as a reference point for all the parabolas we graph. So 0, 0 is on the squaring function because 0 squared is 0. 1, 1 is on the squaring function because 1 squared is 1. 2, 4 is on the squaring function because 2 squared is 4. This is what the squaring function looks like to the right of 0, 0 is half of my u. And then because of symmetry, because I have my axis of symmetry, I know there's a point -1, 1 and -2, 4. And it looks like this on the other side, a mirror image pretty much on either side of the axis of symmetry. So there is the squaring function. What I'm going to do is I'm going to take all of these points and I'm going to multiply their y values by the value of a. Remember, a was -2. All right, a was -2. So let's see what happens here. From the vertex, let's graph this one in blue. From the vertex, which would still be 0, 0, from the vertex, well, if my value of a is -2, 0, 0, the y value, when I multiply it by -2, well, the y value is 0, so I still get the point 0, 0, which is why I made that dot there, that blue dot. So that's the point 0, 0. Multiplying the y value of 0, 0 by -2 still gives me 0, 0. This point right here, 1, 1. Well, if I multiply the y value of 1, 1 by -2, I get 1, -2. So if I take that y value and multiply it by -2, I get 1, -2. So that would be where this point would be stretched to. It would be twice as far from the x-axis, but it would be underneath the x-axis because it's negative. And also, because of symmetry, on the other side, when x is -1, y is also going to be down here at -2. And then, let's see here. There's another point up here, which is the point 2, 4. If I multiply the y value of the point 2, 4, right? I multiply that y value of 2, 4 by -2, it becomes the point 2, 8, because I'm only multiplying the y value, and I get 2, not 8, but -8. Sorry, 2, -8. So I need 5, 6, 7, 8. So I go to 2, -8. 2, -8 is down here. And once again, because of symmetry, I have another point over here at 2, at -2, -8. So I have this on this side, that's half of my u, and this on the other side, that's the other half of the u. And these are going to be the relationships of the points when I graph my function up here. All I have to do is move this graph that I just drew, the blue one, all I have to do is move it horizontally 3 units and vertically 2 units. This is where my new vertex is going to be. So all I have to do is find my vertex and then look at the relationship of the other 4 points to the vertex. Let's go ahead and do that. Right, my vertex was the point 3, 2. So let's graph the point 3, 2. The point 3, 2 is right here. 1, 2, 3, 1, 2. This is the point 3, 2 right here. Okay, so that's the vertex point of the parabola. That's the vertex point. Now from that vertex point, because this parabola is stretched by a factor of -2, all the other points will have the same relationship to the vertex as these points here have to this vertex right here. So that means if I go 1 to the right of that vertex, I should go 2 units down. So let's do that. So here's the vertex. If I go 1 to the right, I should go 2 units down right here. So 1 to the right and 2 units down. And because of symmetry, if I go 1 to the left, I should also go 2 units down. Remember, we have an axis of symmetry that we can use as a guide. Okay, back here. Well, from the vertex, when I went 1, 2 units to the right, I went 8 units down. So over here, same thing. From the vertex, when I go 1, 2 units to the right, I should go 8 units down. So 2 units to the right, 8. Let me scroll down a little bit. So I go 1, 2 units to the right, and I go 2, 4, 6, 8 units down right here. 8 units down. And because of symmetry, also from the vertex, if I go 2 to the left, I should also go 8 units down. Okay, so those are some of the points that are on my parabola. The other thing that I needed to identify were the intercepts. Notice I have 2 intercepts right here, 2x-intercepts. And the y-intercept would be what you get if you plug 0 into the function. So let's try to look at the y-intercept here. We have 5 points already. Let's find some other points. Another thing we were asked for were the intercepts. The y-intercept is what you get when you plug 0 in for x. So if you plug in 0 for x, the f of 0, well, the f of 0, if you plug 0 in here, this would be 0. If you plug 0 in for x here, this would be 0. And we get the f of 0 to be -16. So the y-intercept is the point 0, -16. 0, -16. So let's see. 2, 4, 6, 8, 10. 0, -16 is off of our graph. So at least in the region where our graph is, this parabola will not touch the y-axis. But it continues to get closer and closer. And it doesn't touch all the way down until it gets to -16. And then on this side is a mirror image of that side. So we have this parabola here. Here's a graph of my parabola. This is a graph of the quadratic function. Let's see all the things that we were asked to identify. All right. So we've graphed the quadratic function. There's the graph that we have. There's the graph that we have. It says to identify the vertex. Well, the vertex we found out was the point 3, 2. So let's identify that over here. This is the point 3 comma 2. All right. It says to identify the axis of symmetry. Well, in this case, the axis of symmetry is a vertical line that goes through the vertex. So this vertical line right here would be the axis of symmetry. And that vertical line has the equation x is equal to 3, or like we said, x equals h. So that vertical dashed line I just drew has the equation x equals h. So that's the axis. So I've identified the vertex and the axis, the domain and the range. Well, the domain, if you look at the arrowheads, it means this thing goes forever to the left and forever to the right. But the domain of every polynomial is negative infinity to positive infinity. The domain here then is negative infinity to positive infinity because quadratic functions are just second degree polynomials. It says also to identify the range. Well, the range, if you look at the graph, the arrowheads means that the y values don't begin anywhere. There is no smallest y value. So for the range, we will say the y values have no smallest element, but the largest possible y value is 2. It's the y value of the vertex. 2 is the largest possible y value, and we include it. All right, so we have the domain and the range, and the other thing are the intercepts. Well, I found one intercept, the y-intercept. The y-intercept would be the point 0, -16, like we said, which doesn't appear on the graph here, but this would be the y-intercept. And the x-intercepts are the points 2, 0, and 4, 0. So the x-intercepts are the points 2, 0, and 4, 0. Now, if we didn't have such a nice graph and we couldn't tell what the intercepts were, we could always just use the quadratic formula to find the intercepts. We could take this original function and just apply the quadratic formula to it. Remember the quadratic formula? The quadratic formula said x was equal to negative b plus or minus the square root of b squared minus 4 AC minus 4AC all divided by 2A. This is what you would use to find the x-intercepts if you get a graph that doesn't have nice integer values for the intercepts like this one. Anyway, this is the graph of a quadratic function. The important things that you need to find are h and k. And once you found h and k, A will tell you how much to stretch the squaring function, the primitive parabola, how much to stretch it and whether it's reflected. And then you just look at the relationship between the vertex and the 4 other points and make that same relationship between the vertex that you have shifted horizontally h units and vertically k units and the other 4 points here. Another thing that I wanted to mention was that if you notice, the value of k will either give you the maximum value of the parabola or the function if it's a parabola that opens downward, or will give you the minimum value of the function if the parabola opens upward. All right, so have fun graphing parabolas. This is quadratic functions.